There is no potential difference between the ends of this coil of wire. How then does the bulb glow? A magnetic field gives rise to an electric current in a conductor due to electromagnetic induction. In this lesson, you will learn how electric current is induced due to a magnetic field. At the end of this lesson, you will be able to explain electromagnetic induction through Faraday's experiment, state Faraday's law of electromagnetic induction, use Faraday's law combined with Lenz's law to find the direction of a current, apply Fleming's right-hand rule to identify the direction of an induced current, demonstrate the working of electric generators and explain domestic circuits. You just observed that there was no electric cell to maintain a potential difference across the circuit. Yet, the bulb started glowing. When the wire is moved across a magnetic field, the free electrons in the wire experience a force that makes them move through the wire, inducing an electromotive force EMF, and thus an electric current in the wire. This process of generating an EMF in a conductor by moving the conductor through an external magnetic field is known as electromagnetic induction. When a conductor is moved in a magnetic field or kept in a fluctuating magnetic field, the magnetic flux linked with the conductor changes. This change in magnetic flux induces an EMF across the conductor. The EMF generated in this way is called an induced EMF, and the resulting current is called an induced current. The phenomenon of electromagnetic induction was first studied by Michael Faraday. Michael Faraday hypothesized that current induced in a coil is due to a changing magnetic field. To test this hypothesis, he conducted an experiment. You can observe this experiment to verify Faraday's law. To conduct Faraday's experiment, we will begin by winding an insulated wire over a hollow paper cylinder to make a coil. Next, we connect a galvanometer to the coil. Finally, we insert a powerful bar magnet in the cylinder with the south pole entering the coil first. We observe that when the magnet is moved in, the galvanometer needle deflects towards the left. When the magnet is moved out of the coil, the galvanometer needle deflects towards the right. If the magnet is not moved inside or outside the coil, meaning the magnet is stationary, the needle immediately returns to zero. The deflection of the needle when the magnet is moved in or out indicates that a current has been induced in the coil. Thus, an EMF is induced in the coil due to the movement of the magnet. Faraday's experiment confirmed that a moving magnetic field is necessary for electromagnetic induction. The direction of deflection of the galvanometer needle depends on which pole is inserted in the coil first. For example, in the experiment you saw, if the magnet is inserted with north pole first, the needle will deflect in the opposite direction as that of the previous case. In Faraday's experiment, you observed that a relative change in a magnetic field induces EMF in a conductor. The magnetic field can be changed in two ways: by relative motion between the coil and the magnet, as you saw in Faraday's experiment, or by winding two coils on the cylinder near each other, as shown. In the second case, one coil is connected to a battery with a key. This coil is called the primary coil. The other coil is connected to a galvanometer and is known as the secondary coil. When the key is pressed, a current passes through the primary coil. This current produces a magnetic field. As the magnetic field around the primary coil increases, the magnetic field associated with the secondary coil increases equally. The change in the magnetic field associated with the secondary coil induces EMF in the secondary coil. This EMF can be observed through the deflection of the needle in the galvanometer. The quantum and direction of EMF induced due to electromagnetic induction depends on 5 factors. Let's examine these factors one by one. The first factor is the direction of motion of the magnet in a coil. This determines the direction of the induced current. If you insert the magnet in the coil, the galvanometer needle deflects in a particular direction. When you move the magnet out, the needle deflects in the reverse direction. Thus, the direction of current gets reversed when the direction of motion of the magnet changes. The direction of the induced current in the coil also depends on the orientation of the magnet. If you move the magnet into the coil with its north pole first, rather than the south pole first, the direction of the induced current in the coil is reversed. The speed of motion of the magnet through a coil determines the strength of the induced current. Thus, if you increase the speed of the motion of the magnet, the EMF generated increases, and vice versa. The strength of the magnet is another important factor. The quantum of EMF induced in a coil is proportional to the strength of the magnet. The stronger the magnet, the higher the induced EMF, and thus increased induced current in the coil. Finally, the number of turns in the coil also affects the induced EMF. Using a coil with a greater number of turns increases the induced EMF. Based on his experiments, Faraday postulated a law on electromagnetic induction. Faraday's law states that the induced electromotive force E in any closed circuit is directly proportional to the rate of change of the magnetic flux through the circuit. You can determine the direction of the current induced when a conductor moves in a magnetic field using Fleming's right-hand rule. This rule is also known as the generator rule. To use Fleming's right-hand rule, stretch the thumb, the index finger and the middle finger of your right hand so that they are at right angles to each other as shown. If the index finger points in the direction of the magnetic field and the thumb indicates the direction of the motion of the conductor, then the middle finger indicates the direction of the induced current in the conductor. Consider a conductor AB connected to a galvanometer placed in a magnetic field. The direction of the magnetic field is from the North Pole to the South Pole. When you move the conductor up, the galvanometer needle deflects to the right. This rightward deflection indicates the direction of the current in the conductor from end A to end B. If you move the conductor downwards in the magnetic field, the galvanometer needle deflects to the left. This indicates the direction of the current in the conductor from B to A. Thus, you can see that the direction of the magnetic field, the movement of the conductor and the induced current are at right angles to each other. Electric generators are based on the principle of electromagnetic induction. Generators are used to generate electricity in power plants for transmission and distribution of electricity over power lines, and to produce electric power required for aircrafts, ships and trains. Dynamos used in automobiles are similar to generators, but they produce relatively less power. There are two types of electric generators: AC generators and DC generators. An AC generator is made up of four major components: an armature consisting of a laminated soft iron core with copper windings with a large number of turns, two slip rings made of gunmetal, which are connected to the two ends of a coil and rotate with it, brushes to provide electrical contact between the external load and slip rings, and a powerful horseshoe magnet or an electromagnet. Now let's examine how a generator works. The rotation of an armature, PQRS, between the magnetic poles results in a change in the magnetic flux linked to the coil. This induces a current through the armature. Here is a step-by-step account of how the current is induced. Initially, the coil is vertical with PQ on top and RS at the bottom. This coil is rotated clockwise so that PQ goes down. As the coil rotates through 90 degrees, it becomes horizontal. At this stage, the change in flux with respect to the initial position is maximum. Hence, the current rises from 0 to maximum. The direction of current through each arm can be found using Fleming's right-hand rule. The current flows from brush B1 to brush B2. On rotating further by 90 degrees, the coil becomes vertical again. But now PQ is at the bottom and RS is at the top. The change in flux with respect to the initial position is 0. Hence, the current falls from its maximum in the same direction and becomes 0. Rotating the coil by another 90 degrees causes the current to increase in the opposite direction. Now the coil has rotated through 270 degrees from its initial position. Now, the current flows from B2 to B1. On turning further by 90 degrees, the coil completes one rotation of 360 degrees. The change in flux with respect to the initial position is 0 at this point. Hence, the current falls in the same direction and becomes 0. Thus, the current rises and falls for every 180 degrees of rotation of the coil in opposite directions alternately. The faster the coil turns, the greater the frequency of the current produced by the generator. In an AC generator, the induced current changes its direction periodically and is therefore called alternating current. An AC voltage is continually changing between positive and negative. The rate of change in the direction of the current is called the frequency of the alternating current. It is measured in Hertz, that is, the number of cycles per second. The increase in value from 0 to the positive maximum, then the decrease back to 0, then the further increase to the negative maximum, and the decrease back to 0 is counted as one complete cycle. Like an AC generator, a DC generator also works on the principle of electromagnetic induction. However, a DC generator produces direct current and is commonly used in small-scale power generation devices such as a dynamo. A DC generator is equipped with a commutator, which is a pair of split rings, in a position similar to that of slip rings in an AC generator. A commutator helps in keeping the polarity of the brushes the same to ensure unidirectional current. The other major components of a DC generator are similar to that in an AC generator. A DC generator that contains a loop generates a pulsating DC current. To produce a more stable output, a coil with more turns is typically used. In a DC generator, when the coil rotates through 90 degrees, the change in magnetic flux induces an electromotive force of maximum strength. This current flows through the split rings to the brushes. When the coil is rotated further, at 180 degrees, the electromotive force becomes zero. At this point, the contact between the commutator and the brushes is reversed. The first brush now comes into contact with the second segment, while the other brush comes into contact with the first segment of the commutator. This keeps the current going in one direction. Most of the power plants in the world produce high-frequency alternating current that is supplied to industrial and household consumers through power grids. Electrical components and wires fitted in a household to supply electricity to various appliances form a domestic electric circuit. Let's see how electricity is distributed through domestic electric circuits. A network of overhead or underground cables brings power to our homes. Domestic electric circuits are connected to this network through main supply cables, commonly known as mains. The main supply cable has two wires. The first wire, usually in a red insulation cover, is called a live or positive wire. The second wire, insulated in black, is called a neutral or negative wire. Electric current enters a domestic electric circuit through the live wire. The neutral wire provides the return path for the current out of the circuit. These wires pass through the main fuse in a meter board. A main switch connects these wires to the line wires in the house. Line wires supply electricity to all circuits within the household. Separate circuits may be used for power lines supplying 15 ampere and 5 ampere current. This is to provide for varied current requirements of appliances. Appliances with higher power ratings, such as air coolers and geysers, require a 15 ampere supply. On the other hand, electrical fittings such as bulbs and fans run on 5 ampere supply. Domestic electric circuits also have earth wires used as a safety measure against any leakage of current. In case of power leakage, appliances with metallic bodies such as electric irons and water geysers may convey excess current to a human body in contact. This can result in an electric shock and may, at times, also prove fatal. Connecting the metallic bodies of these appliances to earth wire ensures that any current leakages are conveyed to the earth. Hence, earth wires save users from severe electric shocks. Earth wires are generally insulated in green color. An electric fuse is an important component of all domestic circuits. An electric fuse is a safety device used to protect an electric circuit against excessive current. If your electrical appliances receive very strong current, they could get damaged and stop functioning. To prevent damage from fluctuations in the current, an electric fuse is used in the domestic circuits.